Hello everyone. In this video, we are going to start the topic of relational schema design. Right. So previously we have been covering things like functional dependency theory and projection of FDs, closure, algorithm, and so on. So in this video and in the next video, what we are going to see is that we are going to use all those basic techniques that we have been developing and show how we are actually going to decompose a given schema such that the resulting schema is you know uh, it follows either BCNF or 3NF. Okay, so let's get started. Okay, why do you even want to decompose a schema, or what is the goal of a good relational schema design, right? So one of the things which is of prime importance is that we want to avoid the anomalies and we want to have minimum data redundancy as possible, right? So let's take an example to see what that means here, right? So this is a sample relation. uh, I just made it up to look like a bad relation so that we can argue why decomposition is needed, right? So in this particular relation, so you have this Aadhaar number of the faculty, his address, and the project that he is working on, and the funding institution that funded this particular project, right? And then what is his position, right? Is he assistant professor, associate professor, or full professor, whatever maybe, right? So you can take this as an I'm intentionally giving you a bad relational schema design in the sense that I have put in uh, tuples from the project and the employee table together, right? So for example, if a faculty has more than one project, then his address column will get repeated, and so on and so forth, right? So let's take this example and see what kind of trouble we can get into, right? So first of all, the data is redundant, right? So for example, the address of the faculty is repeated across tuples, so it's basically repeated across all the tuples. uh, so if a faculty has more than one project, then the address information of the faculty is sort of repeated, and so is the position. Okay, and then if there are more than one faculty involved in the same project, so for example here the project CI has two faculty who are working on it, right? A1 and A2, right? So for both these project, for both these copies, the information on the funding institution gets repeated, right? So in a bad relational schema, your data is redundant, right? And then let's say that we have the following functional dependencies in this particular business use case. So one being that given an Aadhaar number, I can uniquely determine the address of the faculty and the position, right? So essentially, I'm saying that Aadhaar number can uniquely identify the details of a faculty, right? So that is why I'll write the FD as Aadhaar number implies address and position. And then for the project, I have the following functional dependency. You give me a project number, I can tell you who is the funding agency. So that means that project number implies funding institution information, right? So these are our two FDs which we'll hold in our this business application that we're trying to model, right? So now when we are having a schema like this, so one thing is that data is getting repeated. There is redundant data storage is going on. That is problem number one. And even if we let go of that problem of data redundancy, you still have more problems to consider. So there is something called as the update anomaly. Now, what is the update anomaly? So let's say that the address of our faculty A1 gets updated. Now you have to change. You have to make sure that you change the address of this A1 faculty in multiple places. Otherwise, what will happen is across different tuples, the faculty A1 will have different addresses. This is what I write. We write here that if the address of A1 changes, we should remember to change this address value in each of his or her tuples, right? So this is called as the update anomaly. Second is deletion anomaly. So let's say that uh, this particular tuple gets deleted, right? So for example, let's say A1, the faculty A1 is no longer working on project C2, right? So let's say the project got reassigned or maybe got unassigned or something happened. Let's say that A1 is not working on the project C2 anymore. So if you were enforcing your database just to store this table, then what would you do? You would have to delete this tuple, right? So when you delete this tuple, what has happened is that if there are other faculty on C2 who are working on C2, then it's fine. But if there are no faculty who are working on this project C2, then you would also be losing the information when if you delete this tuple, you would also lose the information that the project C2 was funded by funding institution D2, right? So this piece of information gets deleted when you delete the information that A1 no longer works in C2. So this is what is called as the deletion anomaly, right? So this is what it is written over here. If nobody else is involved in C2, then we can lose the information that C2 was funded by D2. Okay. Okay. So I just updated this slide over here. When I post it, you'll get the updated slides. Okay. Hold on. Okay. Now, whatever normalization forms that we are going to study, we'll try to make sure that the schema that we get out of this normalization does not have all these problems. The sense that it does not have data redundancy, it does not have update anomalies, it does not have deletion anomalies, right? To the maximum extent possible. Of course, different normalization techniques have different shortcomings, but nevertheless this is what our goal is to hit all these three problems. In addition to this, there is something else also called as lossless decomposition, but for now you set your goal as minimize data redundancy, no update anomaly, and no deletion anomaly as your goals for normalization. Okay, so with that in mind, let's start our first technique. This is called as Boyce chord normal form BCNF. So here we say that we define a relation to be in BCNF if whenever a functional dependency X implies A is existing. So here again, just to remind you of terminology, that X can be a set of attributes. Whenever I write here X, Y, or Z, those are set of attributes, and A is singleton. Okay, so whenever X implies A, it is existing in my relation R, then X has to be a super key, right? And this particular FD should not be a trivial FD, right? So in the sense that the A over here should not be a subset of X, right? So that this is why I say the formal definition is for all functional dependencies X implies A which hold on relation R, then those FDs should be non-trivial FDs, and the left side should be an super key, right? So these are the two conditions. No trivial FDs. Trivial FDs, they don't make much sense, right? So that is why we say that for every non-trivial FD which exists on relation R, the left side should be an super key of R. So that is the definition of BCNF, right? So if on a given relation, let's say you have all these set of FDs which are applicable, then in each of those FDs, of course, these FDs should be non-trivial, and in each of those FDs, the left side should always be a super key of the relation R. Right. So let's see an example. Right. So we're going back to the example that we just covered. Uh, so over here in this sample R relation, we had these two functional dependencies, right? Now, if you try to determine the key, then the only key of this particular relation would be the combination of Aadhaar number and project number, right? So because when you do a closure, attribute closure of this set, you will get all the other attributes, right? So this is the only key of this particular relation, right? Of course, any superset of this will become the super key. Now, if you see the functional dependencies which hold in your relation R, this sample R, the left side, it's not a key, it's certainly not a super key, right? Therefore, both these FDs, they violate your BCNF rules, right? So this is a very formal way of saying that your given relation is not in BCNF, right? And then we saw that it had all those problems. Right? So if you want another example, so let's say this is a relation R1. I have principal investigator name, the address, the project number, and budget. Right. So let's say that I have my FDs as so PI name implies the address. Implies the address. So given PI name, I can determine the address of the person, and given the project number, I can determine the PI who is working on that, who is the principal investigator for that project, and the budget, right? So here there is a bit of an assumption that the for each project there will be a unique principal investigator. Okay. So that is why I say that given a project number, I can uniquely determine the principal investigator and also the budget, right? So we have these two FDs. The only key of this particular relation R1 is project number, right? You can add more over here and that will just become the super key. So PI name is not a key of this particular relation, right? Because PI name cannot determine project number and budget. So in this particular case, what happens is that out of the two FDs which hold on this relation R1, the first one violates the BCNF property, whereas the second one does not violate the BCNF property, right? So the thing to remember is that even if you catch one FD which violates your BCNF property, then that means the whole relation is not in the BCNF, right? So here both of our FDs violated BCNF properties for this sample R. But here only one of the FDs, this FD violates the BCNF property. Nevertheless, R1 is also deemed as not in BCNF, and similarly sample R was never in BCNF to start with. Okay. So this is just an illustration to to show you how to catch the BCNF violations. Now let's say you have the BCNF violation. Now how do you decompose it such that uh, you know you get a resulting schema which is in BCNF. So basically the goal is that let's say you have a big schema containing maybe 10 attributes, and some FDs are there, and you catch that this particular big schema containing 10 attributes is not in BCNF. So what you do is that you pick some FDs and you break and using that you break the schema into smaller portions. Maybe you create maybe 2 or 3 tables out of it, and the goal is to come up with a schema such that the resulting little child schemas which you have created all together, now each one of them actually happens to be in BCNF. And also there is a rule that this child schema, when joined back together, you should get back your original table, right? So that is called as lossless decomposition. We'll get there. To give you a very quick answer, BCNF ensures lossless decomposition. Okay, okay. So no further digressing. Let us go into the algorithm of BCNF. Right. So you are given a relation R, some set of FDs which hold on this R. Right. Now you given a relation R, you first have to determine what are its keys, and there can be more than one key also, right? And then what you do is that you keep going through the this list of FDs F, and you catch an FD such that it violates the BCNF. Note that there can be several functional dependencies in this F which violate the BCNF property. You just catch one of them for now, right? So let's say that X implies B is the functional dependency which you caught, uh, such that it violates the BCNF property. So that means the X over here, it's not a super key of R. Now, so once you have that, what will you do? You will compute the attribute closure of X, right? So you do compute X plus, which is the attribute closure of X, and then you replace the relation R, your original mother relation R, with two schemas. One being this R1, which is basically list of all attributes which are there in your X plus, right? Note that X plus contains X also, okay? And then the second relation would be R minus X plus minus X. Okay, so these are the two relations which you get, right? So the important thing to note over here is that this X, which was used as a seed to create this R1 or to break this relation R, this X stays in both R1 and R2. In R1 you take X and all of its closure once, and in R2 you take out this the closure attributes, but you leave the X here, right? So after you create this R1 and R2, what you do is that you project your given set of FDs, so the original input set of FDs F, you project those FDs onto these R1 and R2, right? And then the process continues until and unless as long as you keep getting an FD where BCNF violations are happening, you keep doing this process, right? So maybe I should write here as a step. So I wrote this last statement that you keep doing this. Now, after you project these FDs, the initial set onto R1 and R2, then you will again check whether R1 was in BCNF or not, or whether R2 was in BCNF or not. If either one of them is not in BCNF, or if both of at least if either one of them is not in BCNF, then you keep doing this. Again you catch an FD such that it is violating the BCNF property, and then you again do the decomposition. You keep doing it until unless you come to a stage where all your children are, all the current set of relations which you have in your decomposition, if they are in BCNF, that is when you stop. Okay, this is just a pictorial representation. It's fine. Okay, so let's go with the example here. So I started with this particular schema, and these were our input set of functional dependencies. So as always, I pick one BCN, one FD which violates my BCNF, right? Okay, so one thing to note here is that depending on what FDs I pick here, the end result might be different, right? So for a given schema, there can be in principle more than one BCNF decomposition. Okay, so here first I pick this FD, Aadhaar and address, right? So what I do compute the closure of Aadhaar, this part, I compute the closure. So what will I get? I'll get Aadhaar number, of course, address, this address, and even the position also comes in. Okay. So now what do I do as per our algorithm? So all of this becomes one sample relation, and in the other relation I put all the remaining items from here and this Aadhaar. So I'll put Aadhaar, project, and funding institution. Okay, so these will be my two relations. Now let us check. Are both of these in BCNF? No. So at this stage, I'm sort of jumping steps here, but ideally, what you would have to do is that you have to take all these FDs and you have to project them onto R1 and R2 to get the set of FDs corresponding to R1 and R2. Right? So at this stage only, you might remember that I was talking about minimal basis. So when you project the set of FDs onto your children relation, right? Let me go to that step. Yeah, project the given FDs onto the new relations, right? So here, after you project, your textbook algorithms, they call for computing the minimal basis, and at that stage only, I said that if you compute the minimal basis after projecting, you will terminate faster, quicker. But even if you do not determine that minimal basis, all you would end up doing is that you will have more iterations of the algorithm. Okay, the answer will not be wrong, but you will have more iterations. Okay, so here on these two sample relation, on these two decomposed relations, I'm going to project these FDs to see which FDs are valid in each of these relations, right? Now, whether you want to, after projection, whether you want to do minimal basis or not, that is, I'm leaving that to you. Okay. Okay. So that step is done, and then we check whether these two are in BCNF or not, right? So okay. Yeah. So that these are the two steps. Okay. So here I'm quickly writing that for example R1, these are the relevant FDs, and but you cannot just write it like this. So here it was a very trivial case, so I wrote it. But in your case, when you have a complicated example, you actually have to use the projection of FDs to make sure that you actually get all the relevant FDs, of which will hold on the children relations, right? Okay, so here this guy is in BCNF. Okay, so that okay. Now the second child of our decomposition step, sample R2 containing Aadhaar, project, and funding institution. This guy, I know this is not in BCNF because uh, the FT that comes over here is project implying funding institution, right? And the only key of this particular sample relation, sample R2, is Aadhaar and project, right? So this here, the left side, this is not a super key. Okay, now the same process repeats. So what you do, you pick the left side of this FD, you compute the closure. It trivially gets project and funding institution. So you now decompose sample R2 into further two pieces, right? So project and funding institution comes as one, and the second one being that all the remaining attributes here, which is just the Aadhaar number and the project number, they all stick together. They both come in the second one, sample R4, right? So our resulting decomposition of our sample R relation is this, are these three relations, right? And intuitively also you can see that this decomposition makes sense, although we arrived at this place algorithmically, But if you see closely, the sample relation R1 is just details about the faculty. What is the Aadhaar number, what is his address, and what is his position in the department. The R3 project is all about, projects. What is the project number and who is the funding institution, and if there were other attributes of the project, they would have also come here. And then sample R4, this is sort of an connector relation between your project and the faculty table, right? So that is this, right? So intuitively also it makes sense how the resulting one, uh, it maintains all the sanity. Okay, good. So this was the BCNF decomposition algorithm. Your textbook also has a very wonderful example. Make sure that you go through it, and I would strongly insist you to practice some problems on BCNF decomposition. Right. So this is a very standard question in the exam. Right. It's a no-brainer. If you know the approach, you can just get 100% on this part. These are the kind of questions where you should not be losing points, right? But if a question comes like this, I'll give you a schema, I'll give you some set of FDs, and I'll ask you to decompose it into BCNF, let's say, right? So you have to make sure that you follow the entire algorithm, right? So one place where people miss is that they do not use the proper projection algorithm. They just intuitively write that these FDs hold on this relation R, right? That is wrong. So here I wrote it because otherwise the slides could have become cumbersome. But in the actual exam, you must use the FD projection algorithm to show that you are indeed getting all the FDs which hold on the decomposed relations. Okay. So with this, I'll stop the this particular video on BCNF. In the next video, we'll take this further, and we'll talk about what how a BCNF is, what kind of problems does it have, is it always good, right? That will be the next video. Okay, thank you.